These ways of displaying images of the modern world all share a common thread, be they computer-generated people or kitchen design, or even glossy advertising logos. You'll see that all these imaging systems rely on linear transformations. Although moving images like this look complicated, when they are broken down into their simplest elements, you can see that they are basically formed from rotating and varying the sizes of straight lines. Methods for displaying images and designs have been promoted by commercial businesses. This store provides a planning service for customers who are interested in building self-assembly kitchen units. Their system relies on linear transformations to draw different views of objects in the kitchen or of the whole room.
Right. You could change this unit.
Yeah, can I change that one into some drawers?
Into drawers.
Yeah.
Got a selection of 5 drawers. A drawer and a door, or 3 drawers.
Right. Can I see what 5 drawers would look like?
That's the 5 drawers.
Yeah, yeah. I like that actually. Can I see the kitchen from a different view?
I'll show you a 3D.
And get some idea of...
So that's your 5 drawers.
Yeah,
here.
I like that. I think that works there, thank you.
So, with this computer system, you can move the objects about at will.
That's your door.
Oh, I see. Yeah.
Okay.
That's great.
But how well do these plans work when it comes to constructing the real thing? Well, here is that Nexus kitchen fully installed. As you can see, it fits exactly into its allotted space. The computer drew just the outline of each item in the kitchen. But now, of course, it's quite solid to the touch. Suppose you wanted to add an extra item to the kitchen, such as this cereal packet, for example. Well, how would you do it? The computer needs to know the position of each of the edges of this box. Well, we first tell it the position of each of the corners. We then need to tell the computer which of these corners to join together with straight lines to form the edges of the box. Well, how do we tell the computer where each corner of the box is? Well, if we take the origin to be the centre of this turntable, for example, then any corner of the box is defined by being a certain distance x along in this direction, a certain distance y backwards, and a certain distance z upwards. Now suppose that we want a different view of the box, so we rotate it through 90 degrees. Well, how does the computer compute this new image? It takes the positions of each of the 8 corners originally and applies a rotation matrix to them. This gives it the position of each of the corners in their new positions. It then joins the same corners as before with straight lines to give the edges of the box. This rotation that we've performed is a simple example of a linear transformation. An important property of linear transformations is that they map straight lines like this edge here to straight lines like this edge here. Well, in this case, we moved the box to get a new picture of it. But of course, we could have moved the camera instead. In that case, as well as getting a new picture of the box, we get a new picture of everything else in the kitchen as well. As you can see, we've cheated a bit and filmed a kitchen in this store, but it's still true to the computer plan. To find out more about the design system itself, Joan Walker visited the software providers.
I'm with Mike Hardman of iCAD, the software designers who have developed this particular computer design tool. So this is the basic plan of my kitchen. Now, how many lines actually go to make this kitchen plan?
Well, there are probably 150 items in the design, and if we take an average of 20 lines per item, that will give us between 3,000 and 4,000 lines in the whole design. I can show that by changing the view to a wireframe, and here we can see every single line in the design.
Right. Now there's a jug on the surface there that looks as though it's made up of a lot of lines. Why is that?
The jug is made up of curved surfaces, and these need to be represented on the screen by straight lines. And I can change my position in the room so that I can get a closer view of that.
Oh, I see.
Okay, we've seen the circular top on the jug. With the cup and saucer here, the curve or the circle on the saucer has been approximated into a number of straight lines. And if I select that item, you can see clearly the divisions in the saucer.
Yeah. Now, Mike, this is the basic detail of my kitchen, but you can be more sophisticated than that with colour and texture, can't you? Can we have a look at that?
Okay. If I move back out of the design so that we've got a wider view, there's the design in the hidden line view. And I can change that so that I can introduce colours and textures. And I can go on to improve the quality.
And I can identify the cereal packet there.
That's right. I can select our cereal packet, and in this area of the programme I can get some information about the packet. And I can see here that its length is 220 millimetres, and I can see its depth and its height, maybe its price if it needs one, and a description at the bottom. I can also find the position of one of the points on the packet in the design with these coordinates here.
And then if you wanted to rotate that object, can you type in the angle that you actually want to rotate it through, for example?
Yes, I've got the object selected, and in the palette on the left I can choose to rotate the object around a particular axis. I'm choosing the Z axis here, and if I just type in 90 degrees, we'll see that when the screen redraws, the object's been rotated.
The next step with computer design systems is to produce images that look more and more lifelike. In fact, this room is not as real as it might appear. It's a virtual world. The objects in this virtual world have been formed in exactly the same way as you saw before, although the room has been embellished with more textures and other subtleties, such as additional lighting and shadow. There are some extras as well, such as an object over there which appears to be a working television. It's not always headline news, but the manipulation of huge sets of data by linear transformations often makes it onto your screens.
The Japanese Prime Minister has introduced emergency measures to combat an outbreak of mass food poisoning, which has so far affected more than 8,000 people. The worst affected area is in the suburb of Sakai in Osaka City, where 6,000 school children have fallen ill over the past fortnight.
Although you might not have thought much about it, linear transformations are used to manipulate computer images of the Earth as part of the news service. Jerry Clark is in charge of the BBC's World and 3D Graphics Unit. So, Jerry, you're called on by the newsroom to devise graphics, such as that move to Japan. How much preparation time might you get?
Sometimes we get 2 hours, sometimes it may only be 10 minutes. It depends when the story breaks.
Now, that move was very, very quick, so maybe it's not as smooth a rotation as you would like.
Unfortunately, most stories are very short. The graphic has obviously got to run whilst the presenter is talking about the story.
Yeah.
So the map move has to be very quick. Indeed, this is a very long rotation. You're going nearly halfway around the globe to get round to Japan. To make that move very smooth, it needs to be done over about 10 seconds, or in video terms, 250 frames.
Can you tell me how you did achieve that rotation?
Right, this is the software we use. It was written in-house for this very purpose. It presents you with a globe and allows you to fly around the globe.
Right.
We can animate something by positioning basically 2 keyframes. The start frame, i.e. here.
Right, and okay, just going around there.
And if we close in on Japan, we can say, right, that's roughly where I want to finish my move, and that becomes another keyframe. We can then put the text on, which becomes another keyframe. So now we have 3 saved keyframes, and the computer will work out the in-between frames from that data. You can see it displaying each frame, a frame at a time. You can see it jerking. It's because the computer can't render each frame in real time, which, when you consider there's about 500,000 triangles it's drawing for every frame, it's doing a lot of work.
Yeah.
Maybe interesting to look at the data and go in very close. And when you get in close, it does look very ragged. Fortunately, most of our world stories, we don't go anywhere near that close to the globe.
If you really wanted to specify a particular rotation or rotations, can you do that?
You can't with this software. It's been designed to make things as simple as possible, and all the details of the rotations are hidden from the user. However, if we look at the same data in a different piece of software, you see we're now back at Japan. If I have a look from the camera view, these orbits here are rotations around X, Y and Z axes. They are in fact directly linked to the rotation matrices that describe the camera position.
The globe, used by the news, has its own coordinate system of axes. 2 at right angles through the equator, and a 3rd running through the poles. Different groups have different conventions for labelling the 3 axes. The vertical axis is often called the Z-axis, although the newsroom system calls it the Y-axis, and labels the other 2 as X and Z. To display the North Pole, the computer creates a view from its camera, looking down from above. The operator can move the camera position. There's no real camera, of course, and the effect of a move from the pole to the equator, like this, is equivalent to rotating the Earth in the opposite direction through 90 degrees around the X-axis. This is the rotation matrix for that quarter turn of the Earth. Matrices are convenient tools for handling data of this sort, and are used all the time in computations. If you take the X, Y and Z coordinates of any point on the Earth and put them into a column matrix like this, then the product of these 2 matrices gives the coordinates for the new position of the point after the rotation. For a different rotation of the camera, such as this rotation about the Y-axis, a different matrix would be used to compute the change to the Earth, which is equivalent to that camera rotation around the Y-axis. Specifying the value of theta, the angle of rotation, defines the values in the rotation matrix.
If we suppose that there was a news story that involved the North Pole, as we can see, and Africa, how would we do that?
Right, to start with, I'll rotate 90 degrees around the X-axis. That will flip us down so we're looking along the equator. You can see Africa's in view. It's not quite central, and I think a rotation of about minus 20 degrees around the Y-axis will bring Africa into the centre of the screen, as you see now.
Great estimation.
Practice makes perfect.
Excellent.
An image of the world might involve millions of straight lines, but at least to rotate the world, you just apply the same rotations to each of the lines. In other situations, you have to move different parts of an object in different ways. There's a computer design system which has been used extensively to create characters in computer-generated feature films. Just the creation of a simple moving figure can be very complicated, because each joint in the body has its own system of axes, and the joints are all interconnected. One of the simplest moves of the body is the rotation of the head, although modelling the head is by no means simple.
So, Lucia, you've got a head on your screen. Can you tell me how that's constructed?
Basically,
We used a series of lines which were then joined together to form a patched surface. This was then modified in order to create the eyes, the nose and the mouth.
Mm-hmm. Now we've got 4 views of this head, haven't we?
Yeah, that's right. This helps us to model, to see what we're doing basically.
So can we do a simple transformation? Can we rotate this head?
Yes, we can. I'll just make this a little bit bigger so you can actually see what's going on here. And if I choose rotate, if I turn the head to the left.
Now, do you keep a record of the movement that you're doing?
Yes, we do. This is stored in our information window, and as we're doing transformations, you'll notice as the mouse is moved and the head rotates, the numbers in the transformation box are actually updated.
Right, so that's telling us the degrees that we're turning through.
That's right, yes.
And if you wanted to, say, rotate through a particular angle, you could type that in as a command, could you?
Of course, yes. Although most designers prefer to use a more interactive approach, which is just to drag it around.
Yeah, so you can see what it looks like.
Yeah, exactly.
So linear transformations can be used to make an artificial head look in different directions. When it comes to tracking real-life heads, angles of rotation are still all important. This is a virtual cockpit, which allows pilots to fly without leaving the ground. The outside world is represented to the pilot as a virtual scene, with video images being displayed in front of each eye using a system of fibre optics. As the pilot moves standard aircraft controls, the response of the aircraft is calculated and the image is updated by applying linear transformations. This virtual cockpit has been developed by the Systems Integration Department at the Defence Evaluation and Research Agency in Farnborough. It's a development tool for creating head-up displays on helmets which might one day allow the pilot to fly in any visibility. To give a realistic view, it's important that the image changes as the pilot's head moves. This system uses a mechanical head tracker, which measures various rotations of the head to see where the pilot is looking. Once again, the head has its own separate coordinate system with X, Y and Z axes, this time with a vertical Z axis and horizontal X and Y axes. Looking up and down is the same as rotating the head around the X-axis. Flyers call this a pitching movement. When the head of the pilot moves in this way, the computed image changes like this. Tilting the head from side to side is the same as rotating the head around the Y-axis, which is directed back into the seat. This is a rolling movement. Finally, looking left and right is the same as rotating the head around the vertical Z-axis. This movement is known as yaw. The angles of rotation are measured by potentiometers. For example, the angle of rotation about the X-axis is measured by this potentiometer near the ear. Once the angles are known, they're entered into the appropriate matrices to compute the new image.
Crashed again.
There are occasions when it's necessary to measure helmet movement inside a real cockpit. This School of Aviation Medicine aircraft is used to perform experiments for the Defence Test Evaluation Organisation at RAF Boscombe Downs. When a jet aircraft, like this Hawk, manoeuvres at speed, the pilot experiences huge forces which greatly restrict movement. And there are times when researchers want to know how much the pilot can view out of the cockpit canopy during different manoeuvres. You can't employ mechanical recording devices in such a small space, much of which is already taken up by the pilot's specialized flying clothing. This is flying gear. Helmet, LSJ, life-saving jacket, flying suit. It can be very bulky, and the RAF is particularly interested in modifications to cockpit design which ease pilot movement. Part of their research relies on linear algebra. This is one of 2 Hawk aircraft used by the RAF School of Aviation Medicine. And the pilot is Squadron Leader Terry Adcock. Terry, hello.
Hi.
Now, there's not a lot of room for manoeuvring here, but you are responsible for testing new design, modification. Now, recently, there have been some modifications done to the ejector seat and, in particular, the head box. Can you tell me about that?
Yes, certainly. What we're trying to do is to achieve a greater freedom of head movement for the pilot, so that he can see more of the outside world without his helmet and the head box interacting. We're somewhat limited what we can do with the head box because it's the functional part of the ejection seat. In fact, it contains a parachute, which is very important. One of the prime areas we're looking at is to try and improve the vertical movement of the head, that's in that sense there. And when I'm wearing the helmet, of course, it interacts with the head box behind. So what we've tried is just to cut away the front face of the head box and increase the angle backwards to try and make more space behind the back of the head, thus allowing the head to rotate further back so you can see out the top of the canopy. That is important because when the aircraft is manoeuvring, you are looking in that direction to clear the area into which you're about to fly.
This is where mathematics comes into play, because the easiest way to monitor a pilot's head movement in flight is to record it on video and then analyse the footage. So, Terry, can you explain this process?
Yes, certainly. We've got a video camera here in the cockpit, and the field of view of the camera takes in my head and sufficient area for it to move around in, plus the top of my body. In order that we can analyse the video and determine my head position, we've actually fitted some reference dots, these large white dots, on my flying helmet. And throughout the sortie, of course, my head position is being recorded. So every time I move my head, be it in a vertical sense, in that fashion, or a lateral sense, in that fashion, and of course the dots are moving on the video frame. And after the sortie, then someone will sit down, go through the video frame by frame, physically measure the position of these dots, record it, and produce the data which can subsequently be analysed.
Analysis of the data took place a short flight away from Boscombe Downs, at the Centre for Human Studies in Farnborough, where each frame of the video was carefully studied by a team of mathematicians.
Well, Andy, you were given the film which they took during the experiment, and your job was to work out from the film the actual movements of the head. So how did you go about doing that?
It was essential to calibrate the whole system and the relationship between the coordinates we find on the screen, where an object lies on the screen here, where it was in the real world.
So it's just knowing the coordinates of the screen position of this one point, is that sufficient to calibrate the whole setup or not?
No, it isn't. You need to start from knowing where the head is in space, as we do here, knowing that its rotation is 0 in all 3 directions.
Right.
And we need at least 3 points off this head. So we would select the point we have there and select other points whose position we know, like the end of the mask here, and clearly visible points on either side of the head, here and here. Coordinates on the screen are measured relative to the top left-hand corner. You can measure the position of the spot by placing the mouse cursor over the spot and clicking it. And as you can see, the left-hand number measures the x-coordinate from the left-hand edge of the window, and the right-hand number measures the z-coordinate from the top of the screen. And as we move the mouse to an alternative position and click, both numbers change. It's better to use more than one image for this, and in fact we had the pilot do some simple manoeuvres, like turning his head so that he was viewing 90 degrees to his left. That's the rotation about the z-axis through 90 degrees, and here we can now clearly see 3 white spots placed on the helmet. We can still take the end of the oxygen mask as a 4th, since it's better to have more points than 3, and so we can do a little bit of averaging, calculating the angle of rotation. In fact, we then did 90 degrees right, 90 degrees left, and we had him looking straight up to complete the calibration sequence.
While we're looking at the screen here, can you tell us what this number in the corner of the screen here means?
This number is the force due to gravity, the acceleration due to gravity going down through the pilot at any moment. It's normally about 1 when you're on the ground, but when you're performing intense aerobatic manoeuvres, it can both go negative, lifting him out of the seat, and strongly positive. And further on in the flight, which is the bit we're really interested in, it reaches 5, 6, 7, 8, and even 9 times the force of gravity.
That's the calibration of the system. But there comes a time when you've just got to try the experiment. But how easy is it to interpret the data from this flight back on Earth?
Well, now we can go to the frames from the selected pieces of the flight that we're interested in with high G on them. Then there we just have to measure again the spots on the pilot's helmet and his head. We know the linear transformation for the rotation of the angles of the pilot's head. Knowing where the spots are on the screen, we can now calculate what the angles of rotation were for the head in space, in the real world.
So you've got 3 unknowns, the angles of rotation about these axes, and we've now got from these points 3 equations in those 3 unknowns which we can solve.
Ideally 4, so 4 or 5, so we've got a little bit spare.
Right, so we actually did a bit of averaging because it wasn't quite accurate.
Correct.
So what were you actually trying to find out in this experiment? Why was it carried out in the first place?
The purpose was to see if one head box was worse than the other, and in practice we did indeed find it was worse in terms of angular rotations.
Right, so they couldn't move their head as far as they could?
They couldn't rotate their head as far. Well, you actually use the word move. Life isn't as simple as that, and he can in fact move from left to right, forwards and backwards, and his head can move up and down. We have to allow for that in our calculations. And that turns it into 6 unknowns, not 3. Right. So we have to be able to locate more points on the head each time.
So what you're actually doing is solving 6 equations and 6 unknowns?
Yes, we were.
That's much more difficult.
You've seen several situations involving rotations. There were rotations of the head, rotations of the globe, and of course rotations of the cereal packet in our kitchen. In fact, there are other linear transformations besides rotations. Another simple linear transformation is the scaling. If you scale this packet by a factor of 2 in the vertical Z direction, you end up with a packet that's twice as tall as it was before. Scale this by a factor of 1/2 and it returns to its original size. Alternatively, you can use linear transformations to reflect an image, or even skew the whole kitchen. In this information technology age, computers are fashioning the way in which we display the world. At the heart of all these computations lies the pure mathematics of linear transformations.